Hello everyone. We are now going to start our lecture on 2.3, which is on polynomial functions and their graphs. Now previously we talked about quadratic functions and their graphs. A quadratic function is also a polynomial function whose leading term has an exponent of 2. So in this function, for example, f of x equals x squared plus 4x plus 1, the leading term, that means the first term in an ordered polynomial, will have an exponent 2 if it's a quadratic function. We'll now go into studying other polynomial functions where the leading term will have an exponent higher than 2. So the leading term could be x cubed or x to the 5th or x to the 6th, x to the 9th, x to the 30th, any exponent which will be higher than 2. We are going to learn some special properties of those polynomial functions, some characteristics, some related theorem, and then come up with some techniques of drawing graphs of those polynomial functions fairly easily. Let's go over the topics that we are going to cover in this chapter. First, we are going to learn to identify polynomial functions, and then we will talk about some properties of graphs of polynomial functions. Determine the end behavior of the graphs. So that means how the graphs behave, how the graphs look like at the extreme ends. Okay. Use factoring to find zeros of polynomial functions, and zeros mean where the graph will intersect with the x-axis. That's what finding the zeros mean. It means the x-intercepts. Okay. When we say find the zeros of a polynomial function, we are actually talking about finding the x-intercepts of the graph of the function. We know we saw how to find the x-intercepts in quadratic functions. The process is going to be pretty much the same, but here especially we will be learning how to use the factoring method to find zeros of x-intercepts. Then identify zeros and their multiplicities. All right, we'll talk about this. I'll explain then what multiplicities mean. Use the intermediate value theorem. Again, this is also something new that you will learn in this chapter, and we'll go into details once we get to that topic. Understand the relationship between degree and turning points, and then finally we should be able to graph the polynomial functions using all the properties that we learned of and all the techniques of factoring and so on that we learned prior to going to graph it. Hello everyone, we will now go through the definition of a polynomial function. What I'm going to do is read through what they have here and then break it down and explain with an example, all right, what they are trying to convey. Let n be a non-negative integer and let a sub n comma a sub n minus 1 dot 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 a sub 2 a sub 1 all the way to a sub 0 be real numbers with a sub n not equal to 0. The function defined by f of x equals a sub n times x to the power n plus a sub n minus 1 times x to the power n minus 1 and so on is called a polynomial function of degree n. The number a sub n is the coefficient of the variable to the highest power, and it's also called the leading coefficient. So, working this with an example, let's say n represents an exponent value. N also represents the exponent that is the highest in the polynomial terms, the highest exponent among all polynomial terms. All right, so let's say n is equal to 5. All right, then the term with the highest exponent will be the leading term. All right, so if n is 5, if the highest exponent is 5, then that term should appear first, and then the subsequent terms will be arranged in descending order of the exponent. So if the first term is x to the 5th, the next one will be x to the 4th, plus the next will be x cubed plus x squared plus x to the 1 plus the last one x to the 0. Now mind you, any number or variable raised to the power 0, all right, is x to the power 0 or y to the power 0 or 2 to the power 0 is 1. All right, that's why we do not see x in the last term of the polynomial often. All right, many times we don't see x appearing in the last term. The last term becomes a constant value. Okay, now each of these terms will also or may also have a coefficient, associated with it. All right, when we do not see a numerical multiplicative to a term, that means the coefficient is a 1. X to the power 5th is the same as saying 1 times x to the power 5. All right, just x to the power 4 is the same thing as saying 1 times x to the power 4, correct? When the coefficient is 1, it's not visible, but we know, or we better know, that it is 1. If it is a value greater than 1, then it's a visible coefficient, and that is represented by a in this notation. All right, so let me, okay, so these terms a to the power n, a to the power n minus 1, they represent the coefficient value. All right, so this could be 3 to the power 3 times x to the power 5th. The next one could be 2 to the power x 2 times x to the power 4. This could be, I don't know, 1 times x to the x cube, where, you know, in that case we will not be writing the 1, so it'll be just plus x cube. Again, the next one for x squared, we may have a coefficient of 3, and then the last one could be 6x, and then the coefficient of x to the power 0 could be 10. All right, but because this is x to the power 0, x to the power 0 is 1. All right, so 10 times 1, we don't need to write x to the power 0, we just write plus 10. Okay, so just remember, all this is trying to say, all this verbiage here, what it's trying to convey is, in a polynomial function, the highest power belongs to the first term. So when you write a polynomial function, arrange it so that the highest power appears in the first term, and then the subsequent terms have a power 1 less than the previous term. All right, now it could be that x cubed may not appear in the polynomial function. It's possible. What that means is the coefficient, if the coefficient of x cubed happens to be a 0, all right, then this will disappear, right? We will have 3x to the 5th plus 2x to the 4th, and then plus 3x squared, and so on. All right. That is possible. However, based on what they are saying here, a sub n, that means the leading coefficient, that is the coefficient of the first term, cannot be a 0. All right. But the coefficient of any other term can be a 0 in a polynomial function. All right. So just remember, because we are going to use the terms coefficient of the leading term. All right, so just keep in mind leading term means the first term in an ordered polynomial, or we sometimes also just say leading coefficient. That means the coefficient of the first term. All right. Now let's look into some general properties of graphs of polynomial functions. All right. Now all polynomial function graphs will be smooth and continuous. So polynomial functions of degree 2. So functions of degree 2 are quadratic functions. So quadratic functions are also included in this property. All right. So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So we'll go into understanding what we mean by smooth. By smooth, we mean that the graphs contain only rounded curves with no sharp corners. So when we were doing the quadratic graph, when we were drawing a parabola, we asked you to connect the points, plot the points and connect them with a smooth curve. That means, all right, no sharp corners. Okay, it has to be a smooth curve. So you cannot have a curve. Let's say we have these points, the intercepts, and then, y intercept, well, a vertex and a y-intercept somewhere here. When we ask you to connect the points in of a parabola, you cannot do it like this. It cannot be like this and then like this, or this has sharp corners. All right, this is not the graph of a polynomial. It could be a graph of an absolute value function, but it's not that of a polynomial. A polynomial will have a smooth shape. All right, so we have to connect, and let me erase this v and connect the dots with a smooth curve. So it's going to be like this. All right, like this. All right, this is smooth, no sharp corners. So that's what it's saying. By smooth, we mean that the graphs contain only rounded curves with no sharp corners. By continuous, we mean that the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. All right, so if we have the points here again, all right, if we have some points, okay, oh God, let me do another one. We should be the points should be connected, all right, not just smoothly but continuously. All right, we cannot have a graph that goes like this and then there's a break and then goes like this and then again like this. This is not a graph that's continuous. All right, this one is continuous. That means we connect all the points between 2 points. All right, there is no break between the points, as in this case. There's a break between 2 points, whereas here it's continuous. That means even though we have just plotted 1, 2, 3, 4 points, it connects all points between these 2 points as well. Any point between these 2 points are also points on the graph. All right. The next thing that we are going to determine about the graph of polynomial functions is how it behaves at its extreme ends. All right. It says here the behavior of the graph of a function to the far left or the far right is called its end behavior. So every graph, every polynomial graph, it's going to be smooth, we know that now, and it's going to be continuous. And there are going to be the two extreme ends of the polynomial graph, all right? And at the ends, at its very end, the graph is either going to drop indefinitely or rise up indefinitely, all right? All the way to infinity, all right? Either its left side could drop and its right end could rise, or both left and right could drop, and so on. So we have to figure out, as part of the process of getting to draw the graph of the polynomial, how the extreme ends are going to look like. All right. So it says here, although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left or far to the right. So what this is saying is that in a polynomial function, the graph at the ends are going to either fall or rise, all right, depending on what the function is. However, in between there can be rise and fall, so we can have waves going in between the two ends. So it could rise, then drop, and then rise again, and then drop again, and then rise again, all the way to infinity. So in between the two extreme ends, there could be several ups and downs going on, all right? But the ends would either be a drop or a rise, or it could be that both ends rise, or it could be both ends drop indefinitely all the way to infinity or negative infinity, okay, without bound. However, in between, the graph can have smooth ups and downs, and so on. And if you remember the quadratic function, in a quadratic function, the first thing that we were asked to determine was whether the graph opens up, the parabola of the quadratic function opens up or opens down, right? That was also observing the end behavior of the graph, all right? But the quadratic function, the parabola, is a far more simpler graph than the graph of other polynomials, higher order polynomials, all right? But there too, we started by determining the end behavior of the graphs, that is whether the graph was opening up or whether it was opening down. And what did we look at to figure that out? The quadratic equation was of the form ax squared plus bx plus c. We were told to look at the sign of the leading term. If a was positive, then it would open up. If a was negative, it would open down. We have to do the same thing in a polynomial function, all right? To determine the behavior of the extreme ends of a polynomial graph, we will have to look at a, which is the leading coefficient of the function. And not only do we look at the sign of a, but also the the highest exponent, that means the exponent of the leading term n. If n is odd, then it's going to follow one direction. If n is even, then it's going to be, the end behavior is going to be of a certain kind. All right, so we'll go into the details of that in the next few slides. So this says the sign of the leading coefficient a sub n, all right, same as what we did for quadratic functions. We looked at the coefficient of the leading term, so the sign associated with a, but here we also look at the degree n, degree meaning the exponent of the leading term of the polynomial function, reveal its end behavior. So the process of determining the end behavior is called the leading coefficient test, because we have to look at a sub n, also a sub n, which is the leading coefficient in a polynomial, to determine whether the graph rises or falls or how the extreme ends behave. So here it says as x increases or decreases without bound, the graph of the polynomial function stated here eventually rises or falls at the ends. All right. Now here we are going to learn how to determine the end behavior of the graphs of polynomials by looking at the leading terms of the function, right? Now to determine the end behavior, all you need to do is focus on the leading term. The leading term is the first term in an ordered polynomial. Ordered meaning the terms are arranged from the highest exponent to the lowest exponent. All right. So n, the exponent of the leading term, is going to be the highest exponent in the polynomial. All right. So there are two things we need to look at in order to determine the end behavior. One is n, which is the exponent, and we have to see whether the exponent n is an odd value or an even value. All right. So first we have to look at the exponent of the leading term and figure if it's an odd value or an even value. Once we do that, we look at the sign of the leading coefficient. So a sub n is the leading coefficient of the polynomial. We have to look at the sign that goes with a. All right. So let's read through the slide and look at the diagrams. All right. For n odd, if n is an odd value like 3, 5, 7, 9, 23, any odd value, if n is odd, then we look at the sign of the coefficient. If the leading coefficient is a positive value, so let me circle that. So if n is odd, n odd, and a sub n is positive, then the graph will have its extreme ends dropping indefinitely to the left and rising indefinitely all the way to infinity on the right. Now, in between the two extreme ends, the graph can go up, increase, decrease, drop, rise. Anything can happen, of course, based on the polynomial that we are working with, but at the extreme ends, if n is odd and leading coefficient a sub n is plus, positive, then it drops to the left and rises to the right, or rises to the right, yes. Now, for n odd, so if n is odd and the leading coefficient is negative, so let me underline the negative here. If it is negative, So n is still odd, but a sub n is a negative value. It has a negative sign. Then still one end rises, the other end drops. But look at this graph. It's the left end of the graph. I'm just trying to pick up my pointer here. The left end rises indefinitely and the right end drops. All right, so if n is odd and the coefficient is a negative value, then it rises to the left, drops to the right. All right, so we are done with when n is odd. All right, now let's look at what happens when n is even. All right, if n is even and the coefficient is a positive value, so let me write that, n even and a sub n is positive, then both ends of the graph rise. All right, both ends of the graph rise. If you remember, if you go back to the quadratic function, then remember if a sub n, the coefficient had a positive sign to it, then it was an upturned graph. All right. And of course, in the case of quadratic functions have the highest exponent, n is 2. So it satisfies n even and a positive, and it was a graph, a parabola opening up. Same thing here, same applies here. Both ends rise. However, because this is not a parabola really, because n is not a square, it could be 4, n could be 6, it could be 8, it could be 10, it could be 24. The graph in between the two ends will have rise and falls. All right. Now let's look at the situation when n is even and a sub n is negative. All right, so let's write that, n even and the coefficient has a negative sign. In the case of quadratic functions, when a was negative, when the leading coefficient had a negative sign, then the graph was a downturned graph, right? Both ends would open down. It was a U opening facing down. Again, same thing here, except that the graph still opens down. The extreme ends point down indefinitely. However, in between the two ends, it rises and falls and rises and falls several times. All right. So that's how to identify the end behavior of polynomial graphs by looking at the leading term. Not really just the leading coefficient, we are also considering the exponent, whether the exponent is even and odd. We cannot just determine the end behavior by looking at the leading coefficient. All right, we also have to look at the value of n and see if it's an odd value or an even value. Here's an example of determining the end behavior of a given polynomial function using the leading coefficient test. All right, so let's see if we can apply the rules that we learned in the previous slide to understand how the graph will behave at its extreme ends. So the function given to us is x to the power 4 minus 4x squared. Now all we need to look at here is the leading term. So x to the power 4 is the leading term, and in this term we consider n which is the exponent of the leading term, so n, but we need to just figure out if n is odd value, if n is an odd value or an even value. So 4 is an even number, so we know n is even. Now, once we have done that, we now need to look at the sign of the coefficient of the leading term, all right, or what's called the leading coefficient, a sub n. So we don't see a visible coefficient of the leading term. So that means the coefficient is a 1, positive 1. So the sign is 1, sorry, the sign is positive, all right? The sign is positive. So when n is even and the coefficient is a positive value, then it will be a graph which will have the extreme ends opening up. Okay. And like we said, in between the two ends, the graph can go up or down several times. All right, but that's what the end behavior is going to look like. The end behavior is going to be a graph pointing up. All right, so it says here, let's read through the solution. The degree of the function is 4. Okay, degree is what the exponent of the leading term is. The degree of the function is 4, which is even. Even degree functions have graphs with the same behavior at each end. The leading coefficient is 1, which is positive. The graph rises to the left and to the right. So it is a graph opening up. Now that we know how to find the behavior of the extreme ends of a polynomial graph, the next thing that we need to figure out are the x-intercepts of the graph, the points where the graph will intersect or cross the x-axis. All right. So zeros are nothing but the x-intercepts of the graph. It's called zeros because if you recall, at the x-intercept, y is always going to be 0, right? At the x-intercept, y is 0. And that's why they call it zeros of polynomial function. So whenever they say zeros of polynomial function, just keep in mind it's the point where the graph touches the x-axis. So it says here, if f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f. F of x again meaning y. The y value would be 0 at the x-axis. These values of x are the roots or solutions of the polynomial equation f of x equals 0. When we were doing quadratic functions and learning how to draw the graph of a a graph of a quadratic function, in order to find the x-intercept, what we did was we set our y equal to 0 or f of x equal to 0 and solve the equation for x. We will be doing the same thing here, all right? And these are some terminologies. We call it zeros, the specific x values where y equals 0, also called the roots or solutions of the polynomial equation. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. All right, so this is just rounding up what we said from the start, that zeros, each x value represents the x-intercept. That's where the graph will touch the x-axis. Now let's go through this example of finding zeros of a polynomial function. The function given to us is f of x equals x cubed plus 2x squared minus 4x minus 8. So recall we said that the zeros are points on the x-axis where the graph will touch the x-axis, and on the x-axis the y value or f of x value will be a 0. So all we do is we replace the f of x with a 0 and solve for x. All right. Now, based on this equation here, based on this expression with 4 terms in it, we can factor this by the grouping method and be able to solve for x. All right. So again, for this course, you do need to be very proficient in factoring. Factoring will often be the first step to several steps to the entire process of solving an equation or solving a particular problem. All right, so if you think you need some review on factoring, then please do that. All right, because you need to be very sound with your factoring, all the different types of factoring techniques that are there in algebra. So we have x cubed plus 2x squared minus 4x minus 8. So what the grouping method does is it groups the terms into two. Since there are 4 terms here, we will group 2 terms together. So let me do that here. So the first group is x cubed plus 2x squared, and then the next one is minus 4x minus 8, and then we are going to factor the 2 groups separately. All right, and then we will come up with the factors. So of x cubed and plus 2x squared, so we are just considering x cubed and plus 2x squared. I'm trying to pull up my pointer here. So x cubed plus 2x squared, x squared is common, so we are going to pull that out, factor that out. So we are going to get x squared factored out from the first 2 terms, and then what's left within brackets would be x. So x cubed divided by x squared is x plus 2, right? X plus 2. Now we look at the other group, which is minus 4x minus 8. So of minus 4 and minus 8, minus 4 is common, right? So we factor that out. And what do we have here? It's going to be x plus 2 within brackets, right? When you multiply it out, you should get back minus 4 minus 8. So you can verify minus 4 times x is minus 4x, minus 4 times positive 2 is minus 8. Also, whenever you pull out a negative sign, the sign within the brackets will change. All right, so that's another way to remember or to make sure that you have done the factoring correctly. But the best thing is to just multiply it and check if you're getting back the original expression. So now that we have factored these groups individually, what we do is we see we have a common factor x plus 2 and x plus 2. So make that one common factor, x plus 2. And the other factor is formed from what we factored out. All right, so just a second. The other factor is x squared minus 4. All right, so let's write that. That's the other factor, x squared minus 4. However, we see that x squared minus 4 can be factored further, right? X squared minus 4 is in the form a squared minus b squared. That's a special factoring that was taught to us in a previous algebra course. right? A squared minus b squared equals a plus b times a minus b, all right? So when we have the difference of squared, then it can be factored as a plus b times a minus b, and x squared minus 4 are the uh, uh, difference of squares. So we can write it as x minus plus 2 and x minus 2, or x minus 2 times x plus 2, doesn't matter, right? So we can further write this factors as x plus 2 times these two, x plus 2 times x minus 2. All right, so that's what they have done here. If you go through their process, you'll see the same thing. I just wanted to work it out and give it a voice to it. So x squared times, they factored out x squared. So continuing with the example of finding zeros, we found that the zeros are x equal to plus 2, x equals to negative 2, and x equals to negative 2. We got three solutions for x, two of which are the same. Now we'll go into a little more in the next slide on it, but basically these are the points where the graph will touch the x-axis. All right, so I'm just going to read through the words in this slide. It says the zeros of f are negative 2 and 2, all right? But negative 2 occurs twice, and again, in the next slide, we will learn a little more about that, what that means, all right? The graph of f shows that each zero is an x-intercept, all right? So we determine the end behavior of this graph, all right, of this particular graph. Or did we not? Yes, I don't think this one we did, but let's do that quickly. All right, because n, we are here trying to determine the end behavior of the graph. All right, so n here is odd, which is a 3, and a sub n, the coefficient, is positive. All right, and when that happens, the graph falls, okay, drops on left and rises on the right. And that's what happened. As you can see, they've drawn the graph dropping on the left end and going up on the right end. So the graph of f shows that each zero is an x-intercept, and it touches the x-axis at negative 2 and positive 2. All right, so negative 2 comma 0 at the x-intercept y is always equal to 0 and 2 comma 0. So let's look at the next slide to learn a little more on what it means when we have the two same values, or even three same values for the x when we solve for when we solve a polynomial for x. Now we'll talk about a special condition called multiplicity and x-intercepts. All right. What does multiplicity mean? In the previous example that we worked, when we found the x-intercepts, we saw that we had three solutions for x. One was a positive 2, and then there were two other solutions which were of the same value. All right, there was an x equals minus 2 and another x also resolved to minus 2. All right, when that happens, because the same value is getting repeated multiple times, we call this a condition of multiplicity. All right, it's called multiplicity. And depending on how many multiples of the same value you have, we refer to it as a zero with multiplicity k. All right, so the x values that we find, all right, the x values we find from solving the equation are also called, if you recall, zeros, correct? The zeros of the function. So we call these multiplicities zero with multiplicity k being the number of times the value is repeated. All right, so in our case here, x equals -2 appears 2 times, so it will be called a zero of multiplicity 2. All right, so k here represents the number of times the same value is repeated. Okay, now it says here, if if R is a zero of even multiplicity, that means if k is zero, is an even value. So if the number is repeated an even number of times, then the graph touches the x-axis and turns around at R. It touches the x-axis and changes direction. All right. If R is a zero of odd multiplicity, that means if, let's say, this was repeated 3 times or 5 times, if it had a multiplicity of k being an odd value, then the graph crosses the x-axis at R. Okay, at R being the value of x, where in this case -2. So regardless of whether the multiplicity of a zero is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. All right, so I think we'll go through an example of this either in this presentation or in a um, separate presentation, but let's see what the next slide says. But for the time being, just know that multiplicity refers to the a situation when an x value has when an x value is repeated a certain number of times, so definitely more than once, and if the number of times it is repeated is an even value, then the graph will change directions. It touches the x-axis and then changes direction and goes down. If it is an odd value, if k is an odd value, then it will cross the x-axis. Right? It will not change direction, it will keep going, but it will intersect the x at that particular value, whatever it is, and then it'll keep continuing. It'll cross it and keep continuing. Okay, good. So here we have an example to work through applying the rule that we just learned on multiplicities. It says finding zeros and their multiplicities. They have given us a function and we see that the function is already in factored form. All right, so it makes things easier for us. We can skip the factoring process because everything here is in factored form. We just have to find the multiplicities of each zero, state whether the graph crosses the x-axis or touches the x-axis, and turns around at each zero. I think in the next slide they have done the solution for us, but let me work it out here. All right, it'll be easier for me to explain because we have some space here to work on. So what we do is we take, now this -4 doesn't apply. All right, we have to make this whole thing equal to 0. So let's pull my pen out here. Okay, so we have -4 times x plus half squared, and then x minus 5 cube. We make f of x, all right, f of x equal to 0. All right, and then we solve for x. Now, because the other side is a 0, minus 4 doesn't matter. All right, minus 4. 0 divided minus 4. All right, let's get rid of this step by step. So we get rid of the minus 4. 0 divided by minus 4 is a 0, correct? So what are we left with? X plus half squared and x minus 5 cube equal to 0. 0 divided by any value is a 0. Value or variable is a 0, right? So now we have two factors. X plus half squared, all right? So what does x plus half squared mean? It means x plus half multiplied by x plus half, correct? X plus half squared means x plus half multiplied by itself twice, correct? For x minus 5 cube, it's the same as x minus 5 times x minus 5 times x minus 5. That's what cube means. X minus 5 multiplied by itself thrice equal to 0. Now we make each of these factors equal to 0 and solve them individually. So we have x plus, and I'll use a different color here where we are solving. So x plus 1/2 equal to 0. Therefore, x equals negative 1/2. Then we have x plus half. Now we are doing the second factor. X plus half equal to 0. Therefore, x is again same value, negative half. Then we have x minus 5 equal to 0. Therefore, x is positive 5. X minus 5 equal to 0. Again, x is equals 5. And then x minus 5 equal to 0. Again, this is the last factor here. Therefore, x equals 5. All right. So here, look at the multiplicity. We have x equals minus half. This 0 is of multiplicity 2, correct? What is the multi here? Let's figure it out. Multiplicity. All right, so minus half is of multiplicity 2. All right, x equals minus half is multiplicity 2, right? And x equals 5, these three, is of multiplicity, okay, times 3, right? Multiplicity of 3. Correct? So we have determined the multiplicities of each 0. It says give the multiplicities of each 0. So multiplicity of minus half is 2, and the multiplicity of 5 is 3. It appears 3 times. It repeats 3 times. Therefore, multiplicity 3. And then it says state whether the graph crosses the x-axis or touches the x-axis and turns around at each 0. So it said previously the rule is if the multiplicity is an even value, then it will turn around. All right, so even, okay, so this is even, therefore it turns around. It changes direction. Okay, whereas in the case of 5, it's odd, therefore crosses the x-intercept. All right, so that's what we figured out. Now let's see if our answer matches with what they have worked out in the next slide. So let's check the solution of our work here. It says we find the zeros of f by setting f of x equal to 0, which we did, right? And we saw that we were left with x plus half squared equal to 0. So we had x equals negative half, right? However, because this is a square, this will be a multiplicity 2, right? X equals negative half is a 0 of multiplicity 2, because just like we did in the previous slide, this is the same as x plus half times x plus half squared. We would have two factors, x plus half. So when you equate each of those two factors to 0, we will get negative half twice. So that makes it a 0 of multiplicity 2. For x minus 5 whole cube, x minus 5 occurs 3 times as factors. So even though here they haven't shown that work, they've just shown x equals 5. But if just remember what we did in the previous slide, we made each factor, there were 3 factors. X minus 5 whole cube means x minus 5 times x minus 5 times x minus 5. So we make each factor equal to 0 and solve for x for each factor. So we would have 3 values of 5 for x. So x equals 5 is a 0 of multiplicity 3. So we also stated the same thing in the previous slide when we worked through the problem. Let's look at how the graph will be now, how the graph will look like. We said that when multiplicity is an even value, in this case minus half had multiplicity of 2, then the graph will change direction. All right, it'll touch the graph at x equals negative half and it'll change direction, it'll go up. So here the graph from left to right was coming down, and then as soon as it touched minus half, it changed direction and started going up again. All right, so that's what was supposed to happen by the rules we learned. All right, so the graph will touch the x-axis at x equals negative half and then change direction. As far as 5 is concerned, if it is an odd multiplicity, in this case odd multiplicity is 3 is an odd value, it's supposed to cross the graph at x equals 5, and that's exactly what happens here. We see that the graph is coming down, and then instead of changing direction, it crosses the x-axis and falls down. All right, now another thing we had learned is, depending on how large the multiplicity is, the graph will flatten. All right, it'll flatten at the intercept. So over here you see that it's as if the graph is touching it 3 times, it's prolonging its stay 3 times at 5, x equals 5, and then dropping. All right, the graph has flattened. And higher the multiplicity, flatter it will be at the intercept. For here we see that the multiplicity, as far as x equals negative half is concerned, the multiplicity was just 2, and you see here it's a sharp, it's not as flat, right? It's a sharp turn. Whereas if this was multiplicity 4, multiplicity 8, a higher multiplicity, we would have seen a more flatter U. All right, a flatter U. So that's the other rule that we learned about how the graph is going to be at the intercept. Okay. Now we learn about a special theorem related to polynomial functions and graphs, which is called the intermediate value theorem. Okay, all right, it's called the intermediate value theorem. I'm going to first read through the words here, and then I'll explain in more simple language what they are talking about. So when I read it, it may not really mean much to you, but just wait for my explanation, all right? It says here, let f be a polynomial function with real coefficients if f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c equal to 0. Equivalently, the equation f of x equals 0 has at least one real root between a and b. All right, now I'm going to break this down and explain to you in more simple terms. All right, so we have here, let me just draw an x and y axis, and I'm going to pick two values, any two values on the x-axis, and let's say the first value is a equals -5, and the other one I'll just name it b, all right, and I'll call it -1. All right, -1 is the b and a is -5, because I'm just using a and b because that's what they have used in the explanation here. All right, so let's say we've chosen a equals -5 and b equals -1. Now if we go back and read the second line of it, it says if a, or rather if f of a and f of b have opposite signs. Now here you see we have the same sign for a and b. That doesn't matter. A and B can be same sign or different sign, that's fine. What they are referring to here is f of A and f of B. That means we input A into the function, and the output that we get out of it, which is called f of a. So what it's saying is, if we input -5 into the function and get a y value, which is, let's say, positive, all right, so that means we plugged in -5 into the function, whatever it was, they haven't given us the function, and let's say it's a y value which is positive, so it'll be a point somewhere on the second quadrant, somewhere here. All right, then we evaluate, we take b, which in our case is -1, we input it into a function, and let's say we get a resulting y value from it, which is negative. So I'm going to find a point on the negative y axis, and let's say our point is the y value at -1. A y value is a negative value, right? This is the negative y axis, so the negative value, y value, is somewhere here. All right, so now we have f of a and f of b, f of -5 and f of -1 with opposite signs. All right, now when that happens, all right, in this interval between -5 and -1, we have y values, which where one is positive, the other value is negative. When that happens, then there is at least one value of c between a and b for which f of c equal to 0. In other words, what they are trying to say is there will be an x-intercept between -5 and -1. All right, so if in an interval, all right, f of a and f of b evaluate to values with opposite sign, then there will surely be at least one x-intercept between those 2 points. All right, because think about it, the a polynomial graph will always have continuity. All right, so to connect from here to here, all right, at some point it will have to cross the x-axis. So it will have at least one value of c between a and b, for which f of c equal to 0. F of c equal to 0 means it's an x-intercept, right? If the y value is 0, that means it's a point on the x-axis. So that's what the intermediate value theorem tells us, that if between an interval of x values the corresponding y values have opposite signs, then we can be sure that there will be at least one x-intercept between that interval. It could be more than one. All right, it could be more than one, but at least one. All right, because to connect from for values between this interval, the graph is continuous, and therefore it at some point it has to cross the x-axis to connect to this point below. All right. Equivalently, the equation f of x equal to 0 has at least one real root between a and b. So the graph better have a real or an x-intercept which is a real number. Real root means an x-intercept which is a real number. Later on, we will go through examples where a polynomial function can have zeros which are not real roots. All right, we'll see that. That's why they specify that it will have a real root. Let's go through this example now on using the intermediate value theorem. It says here, show that the polynomial function f of x equals 3x cubed minus 10x plus 9 has a real 0 between minus 3 and minus 2. When we worked through it, we used values minus 5 and minus 1 in the previous slide, right? Here they've given us a function, a specific function, and the a and b values, the interval values, or the ends of the intervals are at x equals -3 and another one at -2. All right, so let's see what they've done here. We evaluate f at -3, so we need to find f of -3 and then f of -2 and see whether they have the opposite signs or not. All right. So we evaluate f at -3 and -2. If f of -3 and f of -2 have opposite signs, then there is at least one real 0 between that interval of -3 and -2. So they have evaluated this function first using -3 as an input value and then -2 as an input value. So f of -3 turns out to be -42 and f of -2 is a +5. We don't have to worry about what the actual values are. We just need to look at the signs, if they are opposite signs or not. So f of -3 is a negative value and f of -2 is a positive value. That means we can be certain that there's going to be at least one x-intercept between the interval -3 and -2. Okay. So the graph associated with the function on which we applied the intermediate value theorem shows that there is an x-intercept, there is a 0 between -3 and -2, x equals -3 and -2. So we had evaluated the function, this function with -3 as an input, and it gave us a negative y value, whereas when we did when we input -2 into the function, we got a positive y value. Therefore, the sign change shows that the polynomial function has a real 0 between -3 and -2, and we do see that the graph intersects the x-axis between these two x values, between this interval. Now here's a fact about the turning points of polynomial functions and their graphs. So it says here, in general, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. All right, at most means the maximum number of turning points that the graph will have is n minus 1. Again, the degree means the highest exponent in the polynomial function. So what it's saying is, if the degree is 2, all right, so let's see, degree represented by n. If degree is 2, that means if it's a quadratic function, then it'll have 2 minus 1 equals 1 turning point. Okay, and that's turning point. Now, and that's at most. At most means that's the maximum turning points it'll have. That's the maximum turn. It could have fewer, all right, but at most 1 turning point in this case. So if you think about it, the graph of a quadratic function where the degree is n, it is a U graph. Okay, it's a U-shaped graph turned up or down, but it has 1 turning point. All right, this graph has 1 turning point, right? And that's what this this rule is trying to say. If the degree is 3, then the maximum number of turning points the graph will have is 3 minus 1, is maximum number will be 2 turning points. Now it can have fewer than 2 turning points. It can have just 1 turning point as well, but that's the maximum. For a polynomial of degree 6, you can expect it to have 5 turning points at the most. Again, these are max. It could have fewer, but that's the max it'll have. Maximum of 5 turning points, n minus 1. All right, that's what this rule is about. Now that we have learned about the different properties of polynomial functions and their graphs, let's go through, let's summarize them and use them all together in an example. All right, so first we'll go through the steps. All right, a strategy for graphing polynomial functions step by step. So first it says use the leading coefficient test to determine the graph's end behavior. So we begin by first determining the end behavior of the graph by looking at the leading coefficient, which is the first term. So again, to remind you, the leading coefficient test takes into account two things. One is n, which is the degree, and whether it's even or odd, and also a sub n, which is the leading coefficient, and sees whether it's positive or negative, and based on that we determine the graph's end behavior, whether one end is going to rise, the other end is going to fall, or whether both ends are going to rise, or whether both ends are going to fall, and so on. So we have to know those. All right. In tests and exams they will not be given to you, so you have to just remember what the leading coefficient test is and how to apply that. Number 2 says find x-intercepts by setting f of x equal to 0. So in other words, we are trying to find the zeros of the polynomial, the x-intercepts where the graph will touch the x-axis. So find x-intercepts by setting f of x equal to 0 and solving the resulting polynomial equation. If there's an x-intercept at r as a result of x minus r to the power k in the complete factorization of f of x, then if k is even, the graph touches the x-axis at r and turns around. If k is odd, the graph crosses the x-axis at r, and if k is greater than 1, the graph flattens out near r comma 0 at the intercept. So let me just summarize this or explain this a little bit. Here they are talking about the multiplicity. All right, we first find the x intercepts, and then we see how many values we got which are identical. All right, and we call that multiplicity, correct? We call that if a solution of x occurs more than once, we refer to it as multiplicity. And if the multiplicity is an even value, that means if an x value is repeated an even number of times, then the graph will change direction, it turns around. If the x value occurs an odd number of times, then the graph crosses the x-axis, right? And if k, all right, the number of times the multiplicity occurs is greater than 1, then the graph flattens out. So I showed you in an example, so you may want to uh, rewind and check back if you need to, but basically this is talking about the multiplicity of the zeros of a function. Going on to the next step, it says we find the y-intercept by computing f of 0. We did that with quadratic functions, remember? We need to find the y-intercept, and at the y-intercept x is 0, so all you do is plug in 0 into the function for x and evaluate it. That'll give you the y-intercept. And then use symmetry if applicable to help draw the graph. Now, this is again going back to, I think, chapter 1, y-axis symmetry. So y-axis symmetry means if you input negative x into f and get back the same function f of x, then that means it's a y-axis symmetry. If you replace x with negative x and end up with a function which is negative f of x, then it's a symmetry about the origin. And we'll go through an example of that, all right, and it'll be more clear at that time. Finally, use the fact that the maximum number of turning points of the graph is n minus 1, n being the degree of the polynomial function, to check whether it is drawn correctly or not. So by following these steps, we should be able to graph a polynomial function fairly quickly or relatively quickly and easily. Now the remaining slides in the presentation are on an example of graphing a polynomial function using all the rules, all the facts, all the theorems that we learned so far and applying them. So let's look at the function they have given us for which we have to draw the graph, going through the steps one by one. So it says here f of x equals 2 times x plus 2 whole squared times x minus 3. As you will note that the form of the function is not in the standard polynomial form. They have given us the function in factored form. Now it's going to make some things easy for us, especially in solving for x, to find the x-intercepts, to find the zeros of the polynomial, but it's a little bit tricky to determine the leading coefficient, and the leading term, the value of n especially. All right, so I'm going to explain that a little bit, but just note that the form given here of the polynomial is in factored form. All right, to get it in proper polynomial form, we need to multiply these out, and then we'll get the regular standard polynomial form of the function. All right, but we don't need to do that to draw the graph. So the first step was to determine the end behavior of the graph. That's what we learned first when we started the presentation. All right, and to determine the end behavior, we said we have to look at what's called the leading term of the polynomial, and in the leading term well, let's say the leading term is in this form: a sub n x to the power n, right? So we had to look at n and determine if it's odd or even, and based on that we would go to the next step of checking the sign that goes with the leading coefficient a sub n. So in the next step we will have to check, after we determine whether n is odd or even, we will check if a sub n is positive or a negative quantity. Okay, now what is n? Okay, how now? If you say n is 2, that's not correct, all right? Because for the simple reason that this is not in standard polynomial form. In order to get the value of n from a factored form, what you should do is you should add all the exponents of the factors. All right, you should add all the exponents of the factors. So in the first factor, all right, in the first factor, x plus 2 squared, we have 2, all right, for an exponent, and in this factor x minus 3 we have 1, correct? The exponent is not visible, but it is 1, right? You can understand that. So we add that up. 2 plus 1 is 3, correct? So n equals, I'm going to write here, n equals 2. You have to take this 2 plus 1, this 1 here, the 1 which is the exponent of x minus 3. So when we add them up, n equals 3. All right, so n equals 3 means n is odd. Okay, if n equals 3, that means n is an odd quantity. Now that we have determined that n is an odd quantity, we go to check the sign that goes with the coefficient. The coefficient is 2. All right, the coefficient is 2, so that's even. I'm sorry, no, it's not about even. Coefficient is 2, that means that's positive, right? So let me write that. A sub n equals 2, therefore it's positive. So when n is odd and the leading coefficient is positive, that means the ends, the extreme ends, will be like this. All right, now anything can happen in between the two ends. So on the left hand side, we see the graph drops indefinitely. Let me pull up my pointer here. The graph drops indefinitely on the left hand side. On the right hand side, it rises up indefinitely all the way to infinity. All right, so that's what the behavior of this function is going to be at its ends, at its extreme ends. So I'm going to read through step 1. It says determine end behavior. Identify the sign of a sub n, the leading coefficient, and the degree n of the polynomial. So a sub n is 2. That's what we said 2. And n equals 3. All right, so here too they use 3 for the value of n. And I just explained here how they get 3. All right, you take, because it is in factored form, again, because it's in factored form, you have to add up all the exponents to get the leading exponent. And then it says the degree 3 is odd, the leading coefficient 2 is a positive number, n odd, and a sub n is positive. The graph will rise on the right and fall on the left indefinitely. We will now talk about step 2 in the process of graphing a polynomial function. So step 2 is about finding the x-intercepts or zeros of the polynomial, zeros of the function, by setting f of x equal to 0. Now, if the function is in the standard form, of the polynomial, then we will have to use different methods for solving for x. We first would need to put the polynomial in factored form, and then we can use the zero factor property to solve for x. Now later on in subsequent sections, we will also learn if the polynomial is not factorable, what techniques to use to find for x. But here in this particular section, they will give us problems where the polynomial is factorable. Now, fortunately for this particular problem, they've given us the polynomial in factored form. So we do not have to do the factoring. All right, all we do is we will just use the zero factor property to solve for x. So let's look at this. We have 2 times x plus 2 whole squared times x minus 3. So we make one side equal to 0 for f of x, and then we will apply the zero factor property. All right, so here they haven't shown the steps of applying the zero factor property, so I'll work it here so it's easier for you to follow. So here we have 2 times, now x plus 2 whole squared is same as saying x plus 2 times x plus 2, correct? X plus 2 whole squared means x plus 2 is being multiplied by itself twice. And then we have x minus 3, appears once, it's x minus 3 to the power 1, so we have to write that, equals 0. Now to get rid of the 2, I'm going to divide both sides by 2. All right, that way we get rid of the 2. I'm just showing the step-by-step process of applying the zero factor property. All right, so now we are left with, and the other side is 0 divided by 2. 0 divided by any value or any variable is always going to be 0 as long as the denominator is not a 0. Okay, so let's continue. We have here x plus 2. All right, we have x plus 2 times x plus 2 times x minus 3 equal to 0. All right, so now take each of these factors and make them equal to 0. So we will have x plus 2, the first factor, equal to 0, equals 0. Therefore, x equals negative 2. Then we have this second factor, which is x plus 2. Just a second, I lost my pen here, so bear with me. X plus 2, that's the second factor, equal to 0. Therefore, x equals negative 2. And lastly, we have x minus 3 equal to 0. Therefore, x equals positive 3. And now we have to determine the multiplicity, if any. All right, we see x equals negative 2 occurs twice. So we have the same solution for x repeated twice. So that makes minus 2 a multiplicity of 2. So x equals minus 2 is of multiplicity 2. Multiplicity 2, right? 2. And x equals 3 is of multiplicity 1, right? It occurs only once. So here we go. X equals negative 2 is a 0 of multiplicity 2, and x equals 3 is a 0 of multiplicity 1. So figured out the multiplicity, and then we have to look at the multiplicity if it is an even multiplicity, as in the case of x equals negative 2. If it is an even multiplicity, then that means the graph is going to change directions at the intercept. All right, so it's going to, and let me just draw the axis here. What it means is, because the multiplicity, whenever the multiplicity is an even multiplicity of minus 2, what the graph is going to do is it's going to touch the intercept, and then it's going to change direction. So if it is a rising graph, we don't know what it's going to be. If it's a rising graph, then it's going to drop at that value of the intercept. If the multiplicity is odd, then it's going to cross the x-axis, all right, the intercept. Now here we've started sketching the graph with whatever information we have learned so far about the graph of the polynomial function. All right, we talked about the behavior of the extreme ends of the graph, where we said that it's going to fall indefinitely to the left at the extreme end, and it's going to rise indefinitely on the right. Okay, so they've started, this is not the complete graph, they just started sketching it with the information that we have so far. All right, so the end behavior is shown here, and now we have to use the information about the intercepts and the information about the multiplicity. All right, so x equals -2 is the zero of multiplicity 2. That means it's going to touch the graph at -2, and because the multiplicity is even, it's going to change direction and go in the opposite direction. All right, so the graph touches the x-axis at x equals -2, flattens and turns around. The other intercept is at x equals 3. It is a zero of multiplicity 1. Correct? That means it's going to cross. It's an odd multiplicity, so it's going to go across the x-axis. So the graph crosses the x-axis at x equals 3. So now the remaining part is to determine how the graph will behave in between. All right, in between these ends. Now we are at step 3 of the process of graphing the function. Step 3 says find the y-intercept of computing f of 0. Again, at the y-intercept, x is 0, so all we do is we plug in 0 for x into the function and do the evaluation, and that's what they've done here. They have replaced x with 0, and wherever there was an x in the function, they replaced that with 0 as well, and we got a value of -24. That means the graph will cross the y-axis at -24, somewhere between -20 and -30, right? So that's where the y-intercept is. So the graph passes through the y-axis at 0, -24. So what they did was they took the graph that we had drawn so far, and now you see that after it changes direction, all right, we have to adjust this section of the graph to cross the y-axis at -24. All right, and then the remaining part now is how it is between these 2 points. All right, this gap needs to be filled in the graph. So we are almost there now. So we are at the point where we need to close the gap in the graph between x equals 1 and x equals 2. Now to do that, we are going to apply that special theorem we learned. It was called the intermediate value theorem, right? If you recall, it was called the intermediate value theorem. And what did that theorem say? It said that if we have an interval on the x-axis, right? Let's say we have an interval 1 and 2, right? If f of 1 and f of 2, if f of 1, I'm just restating the theorem, applying x equals 1 and x equals 2, all right? So if f equals 1 and f equals 2, if they have opposite signs, if the values f of 1 and f of 2 have opposite signs, then that would mean that there is an x-intercept somewhere in between this interval. All right, that means a 0 exists somewhere, a 0 of the polynomial. In other words, the x-intercept exists somewhere in between 1 and 2. That's what the intermediate value theorem says. So let's see what they've done here. They have done the same thing. They have calculated f of 1 by plugging in 1 into the polynomial, and they came up with -36. They've done the same thing with f of 2. They have plugged in 2 into the function wherever there was x and did the evaluation, and they came up with negative 32. And then we note the sign of the two function values. F of 1 is negative, f of 2 is negative. That means they are not opposite signs, they are the same signs. So that means that there is no x-intercept in this interval. There's no x-intercept in this interval. So the graph remains somewhere below. All right, both are negative. That means the graph will remain somewhere below for that section, for the interval 1 and 2. So now let's look at the next slide. So from the intermediate value theorem, we know now for sure that between 1 and 2, all right, 1 and 2, the graph is not going to go up to the x-axis by any means. All right, it's going to stay, it's going to linger on the negative y-axis area. Okay, so step 4 says use possible symmetry to help draw the graph. Our partial graph illustrates that we have neither y-axis symmetry nor origin symmetry. How do we figure out the symmetry? If f of negative x equals f of x, let me write that down. If f of negative x equals f of x, then it's symmetrical about the y-axis. So it's y-axis symmetry. If f of negative x equals negative f of x, then it's symmetry about the origin. Okay, and when we check on that, we see that it's neither symmetrical about the y-axis nor is it symmetrical about the origin. So all you do at this point is to just connect the gap between 1 and 2 with a smooth curve. All right, with a smooth curve. And finally, in the last graph, we will use the information that the maximum number of turning points of the graph is n minus 1. All right, n being the exponent of the leading term, to check whether it is drawn correctly or not. So maximum number of turning points should be n minus 1. Recall that n, with the value of n that we use to determine the end behavior, is the same value for n, which is, it was n equals 3, correct? It was n equals 3. So the maximum number of turning points would be 3 minus 1 equals 2 maximum turning points. It could be less than 2, but 2 is the max. So let's look at the turning points over here. There's a turning point at negative 2 at the x-intercept, and then it turns again over here somewhere between 1 and 2. So that satisfies this condition that the maximum number of turning points of the graph is n minus 1. It satisfies this condition, this rule here about the turning points. So that concludes this particular chapter, and then in the next chapter we'll talk a little more about graphing polynomial functions, but they will address some different kinds of polynomials, all right, which are not necessarily factorable. So stay tuned for that lecture.